The colonization of Saturn's moon Enceladus is an interesting and highly speculative concept. As of now, Enceladus remains a target of scientific interest primarily due to its unique geological features, potential subsurface ocean, and the discovery of organic molecules. However, there is no current plan or even immediate proposal for colonizing Enceladus. Instead, research focuses on studying the moon for its potential to host life, its resources, and its general characteristics. That said, here's a detailed look at the challenges and considerations involved in colonizing Enceladus based on current scientific knowledge. Enceladus. Overview. Enceladus is one of Saturn's icy moons and is about 500 kilometers, 310 miles, in diameter. Despite its small size, it has a number of features that make it a fascinating target for exploration. Water plumes. Enceladus is known for its geysers that erupt from a subsurface ocean beneath its icy crust. These geysers shoot water vapor, organic molecules, and salts into space, which have been studied by NASA's Cassini spacecraft. Potential for life. The subsurface ocean, warmed by tidal forces from Saturn's gravity, could provide the conditions necessary for life, making it an intriguing target for astrobiology. Surface conditions. The surface of Enceladus is covered in ice, with some areas appearing to be relatively smooth while others are cratered and deformed by tectonic activity. Challenges to colonization. To colonize Enceladus, humans or robotic explorers would face numerous significant challenges. Extreme environment. Temperature. Enceladus is located in the outer solar system, with average temperatures around 200 degrees Celsius, 328 degrees Fahrenheit. Such temperatures are far too cold for humans and most Earth life without sophisticated life support systems. Radiation. Enceladus orbits Saturn, which is in the powerful radiation belt of the planet. This radiation could pose a serious risk to colonizers, requiring robust shielding for any spacecraft or habitat. Distance and transportation. Distance from Earth. Enceladus is about 1.2 billion kilometers, 746 million miles, away from Earth. With current space technology, travel to Enceladus would take several years, making the journey long and resource-intensive. As of today, no spacecraft have been able to visit Enceladus directly, aside from the Cassini mission that observed it from orbit around Saturn. Transportation technologies. Technologies for fast and efficient space travel are still in their infancy. Colonizing Enceladus would require advancements in propulsion systems, such as nuclear or ion propulsion, to reduce travel time. Atmosphere and life support. Lack of atmosphere. Enceladus has a very thin exosphere composed mostly of water vapor, which is not breathable or protective. Colonists would need airtight habitats with artificial atmospheres. Oxygen and nitrogen. Enceladus' environment lacks breathable air, so colonists would need to transport oxygen or find ways to produce it on site, possibly through processes like electrolysis or extraction from water ice. Resources. Water. While Enceladus has water in the form of its subsurface ocean and the water vapor erupting from its geysers, accessing this water would be technologically challenging. Extracting it from the ice or vapor would require drilling through thick layers of ice and dealing with low temperatures. Energy. Solar energy would be far less effective at such a distance from the Sun. Colonists would likely need alternative power sources, such as nuclear reactors or geothermal energy if there is sufficient heat from the Moon's interior. Surface and habitat construction. Building on ice. Enceladus' surface is made of ice, so constructing buildings or habitats would require innovations in ice engineering. Structures would need to be insulated to prevent freezing and could be buried beneath the ice to protect against radiation and temperature extremes. Pressure and gravity. Enceladus' gravity is about 0.1 times that of Earth's, which could lead to health concerns for long-term colonization, such as muscle atrophy or bone density loss. Artificial gravity might be necessary for permanent habitats. Communication delays. Latency. Due to the distance between Earth and Enceladus, communication signals would take a significant amount of time to travel between the two, up to 1.1 hours each way. This delay could pose problems for real-time communication and decision-making in emergency situations. Potential strategies for colonization. While colonizing Enceladus is unlikely in the immediate future, it could theoretically be done in stages, building on existing and future technological advancements. Scientific exploration first. Before colonization could occur, extensive robotic exploration would be necessary to understand Enceladus' geology, its subsurface ocean, and its potential for resources. This could involve drilling missions, sending probes or autonomous robots to drill through Enceladus' icy crust to access the subsurface ocean and gather data about the potential for life or habitable conditions. Astrobiology missions. Using the data collected from Enceladus geysers to assess the potential for life in its ocean, including searching for microorganisms or signs of biochemistry. Robotic colonization. In the early stages of colonization, robots and automated systems could be used to build habitats. Robots could construct underground or insulated habitats to protect against radiation and temperature extremes. Mining and resource extraction. Robotic systems could mine water and minerals from Enceladus' surface, providing resources for future human settlers. Human habitation. Eventually, if humans were to settle on Enceladus, they would need to transport supplies. Regular cargo missions would be required to send food, equipment, and other essentials to the colony. Sustainable ecosystems. The colony would need to be self-sustaining, possibly using hydroponics and closed-loop life support systems to recycle air, water, and food. Terraforming. In the distant future, it is possible that advanced technologies could be employed to modify the environment of Enceladus to make it more hospitable for human life. This would likely involve creating an artificial atmosphere, increasing temperatures, or using large-scale engineering projects to melt portions of the icy surface, though this is speculative at best. Astrobiological considerations. One of the primary reasons Enceladus is studied is its potential to host life. The subsurface ocean beneath its icy crust could harbor microbial life, which may be a key factor in determining if colonization is even feasible. Ethical concerns. If life exists on Enceladus, ethical questions would arise about contaminating or disrupting its ecosystem. International space law, particularly the Outer Space Treaty, could prevent human intervention until we better understand the Moon's potential to support life. Conclusion. Colonizing Enceladus is a daunting and highly speculative challenge. Although it is a captivating goal due to its potential for water, organic molecules, and astrobiological interest, it would require overcoming immense technical and environmental hurdles. Advances in space travel, life support, and resource extraction technologies would be necessary, along with an improved understanding of Enceladus conditions. For now, exploration and scientific missions are the most realistic path forward, with colonization likely being far off in the future, if at all feasible.